Hi, you guys. Hope everybody's doing well. I'm sorry this has taken so long. First, I had to wait for the whiteboard to arrive. Then I had to wait for the SD cards, which stands for social distancing. Those came on Sunday afternoon. Yesterday, I did all of this and realized that I forgot to hit record. So, I did my calculus, but I didn't do my pre-calc. So, here we go. Because I'm just using YouTube Classic, it's going to be in like 10 to 15 minute clips. And all of the materials will be supplied to you on CourseWeb. I really miss you guys. Okay, so you're in my bedroom. And this gave me a reason to take a shower and get out of my daytime pajamas. Okay, so this is, we're just going to get your math brain warm by going over what we did before our lovely break. Okay, so we were talking about compound interest and with money. And this was our equation. Remember that this is not a times t, this is a function. This is a of t, like f of x. So this is the amount at time t. So this is our ending amount. A sub naught, that's your beginning amount. In this case, the original investment, or what's also known as the principal. That's a 1. R is the annual percentage rate, the APR, written as a decimal. So if you have, say, 7.5%, it's 0.075. If you have 10%, it's 0.1. N, both of these n's, that's the number of times the compounding is done in 1 year. So if it's annually, n is 1. If it's monthly, n is 12. Weekly, it's 52, etc. T, that's the number of years. For periodic compounding, the time is always in years. Okay, so this is just an example, and we'll do a few compounding things, and then I think that'll get your math brain warm, hopefully. You're going to want to get your calculator if you didn't get it yet. Okay, so here's our situation. We're investing $1,000 over 15 years, not going to take anything out, don't put anything else in. Interest rate is 6.3. If it's compounded annually, and I'm trying to find the ending amount, okay, so A, after 15 years, with an original investment of $1,000, and 6.3% is 0.063, and annually is just 1, so our N is just 1, so you wouldn't bother to write it, but, you know, just to make it easier for you to understand. Okay, so here I have 1.063 to the 15th power times $1,000. Okay. Remember, I'm not fussy about rounding. I don't care about the cents for this stuff. We'll be here forever. But units do count. So if our answer is money, you got to put a dollar sign. Okay. So now, if I have the same situation, $1,000, 15 years, 6.3%, and the compounding is going to be monthly. Okay, so I'm still looking for the amount after 15 years, still starting off with my A sub naught of $1,000, still 0.063. So the only thing that changes is our N, the number of times it's compounded in 1 year. So monthly is going to be 12, and then I have 12 times 15 years. What I do is multiply those two first. Okay, so that's 180. That means it's 180 times over the 15 years that interest is going to be calculated and added into the account. So I do that first, so I don't have to worry about it. Next thing I'm going to do is take 0.063, divide by 12, and then add 1 to it. Take whatever you have in your calculator to the 180th power, and then multiply by your $1,000. Okay, so it would make sense that this one would be a little bit more than that one because the interest is being calculated more frequently, even though it's the same annual rate. Okay. Now, if I take a look at this part of it, okay? If I want to say, okay, I'm going to let R, my APR equal 100%. Okay, this is for the sake of argument. Okay, and I'll let T equal 1 year, okay? What happens as n goes towards infinity? Okay, so, compounding monthly, weekly, daily, how about every hour? What about every minute? What about every second? So as n gets bigger and bigger and bigger and bigger, and I'm using 100% because it just makes the calculations easier to write. So if I say we have 1 plus, and 100% would just be a 1, okay, over 1 to the 1. Well, 1 plus 1 is 2 to the first power is 2. Okay? What if n is 10? Now I have 1.1. Okay, 1.1 to the 10th power. Going to be 2.59 and some other decimals. Okay, what if n gets even more frequent? What if you do it 100 times a year? So you have 1 over 100, that gives us 2.7048. Okay, what if I do it 1,000 times a year? That gives us 2.717. What about if I do it 10,000 times in a year? Which that's a lot of times. That's several times a day, right? That gives me 2.718. If I put 100,000 here, and 100,000 is my exponent, it's going to be 2.71 something. So just going further out, it'll be 2.718 and then some number. So what this is leaning towards, as n goes towards infinity, the entire value of this compounding goes towards 2.71. Remember what that is? That's E. Okay, remember E, our exponential function, after Euler, the guy who figured out this stuff. This is a constant, irrational number. Irrational, never-ending, non-repeating decimal, much like pi. It's not a variable, it's a number, okay? And it occurs with such frequency that it warrants having its own button. And remember, the natural log is log base E. So we're going to be using that a lot. So now, what we have is, if I use this, and we have continuous, sometimes called exponential. Okay? Now our equation is going to look like this. A of t is equal to a sub naught e to the kt. Okay, so we're going to have two equations, and that's all we're having for this section, so don't get overwhelmed. It's just this one and this one. Now, with this one, the time is always in years. For continuous, the unit of time is whatever's given. If you're studying, say, bacteria growth in a petri dish, it's probably by the hour. You're not looking at always a year. It would be overwhelmed and disgusting. Right now, with coronavirus, we're looking at days. And I guarantee all over this planet, they're using this equation. So that's pretty sad, isn't it? All right. That equation is easier to use than is this one. I'm going to write it up here so we can refer to it. Okay. So this is real data. It's unfortunate, but this is real data. In Pennsylvania, on Saturday, okay, so Saturday, in Pennsylvania, we had 371 infections of COVID-19. On Sunday, midday, both of these are midday, we had 479 infections. Okay, so if I want to project out and say, okay, what can I anticipate is going to be in another week? Okay, if that's how much it grew in a day, how much is it going to be by next Saturday? Okay? Okay, hopefully you remember some of the stuff that we did before break. But these are two-part questions. So you use this information to find the growth rate, and then you take that growth rate to answer the question. So here, okay, my ending amount would be the Sunday amount, starting with my beginning amount that was on Saturday. I have my E. K is my unknown, and my T is 1 day. So I don't have to put a 1 there, okay? So this is really actually very simple algebra stuff. So first thing we're going to do is divide both sides by the 371. Okay, so we get 1.29 and change equals e to the k. Okay, do you remember how we solve for a variable in a funky position that is an exponent? Good, everyone got it right. Oh, this sucks so bad, you guys. Okay, so we have to take the natural log of both sides. So, hopefully you remember some of this. And the whole point of taking the natural log of both sides is so that I can bring this exponent out front and then it won't be in a funky position. Okay, so I have the natural log of 1.29 equals k natural log of e. Do you remember what the natural log of e equals? 1. Good job, guys. Okay, so k is the natural log of 1.29, which is crazy. This means 25% per day, exponentially. So, that's a lot. All right, so let me write that here. So our K is equal to 0.25. Now, I'm going to use that to answer the question, what can I anticipate for Saturday? So we're going to take a look at Saturday and Sunday. Okay. So first let's do Saturday. We'll do next Saturday. Okay, so A, if I'm going from Saturday to Saturday, that's 7 days. With my beginning amount of 371, my K is 0.25, and my T is 7 days. Okay, so we want to start here. You're going to multiply 0.25 times 7. Okay, that gives us 1.75. Okay, then we take e to that power and multiply it by 371. And we get which is roughly the size of the enrollment at UPG. That's pretty horrible. Okay, now, just to show you how this works, let's do next Sunday. By the way, I'm really allergic. It's like serious pollen going on. Okay, so now you have two choices, okay? We can use this as my a sub naught, in which case my t would be 8 days. Or I can use this as my a sub naught and my t would be 7 days. Either one, but you want to be consistent. The number of days to the one we're trying to anticipate, you want to make sure that you're using the correct one. So we could have a of 8, starting with 371, or you can have a of 7 with your a sub naught is 479. Okay, so just because in the first part when we calculated this, we used this as our a sub naught, this is a whole separate calculation. Okay, so you just want to make sure that it makes sense. You should get the same answer either way, except for the rounding. Okay, so this would be 2,741 infections. And this one gives you 2,756 infections. The reason why those are different is because I rounded here. Okay, the K actually had loads and loads more decimals with it. So the more decimals, the more those numbers are going to converge. But you could take, excuse me, the mean or the average of those two by adding them and divide by 2. But it'll be interesting to see how close this is. There's just one more thing I want to explain about this part. This is based on uninhibited growth, which means there's nothing stopping it. Something that would inhibit growth of an infection like this would be obviously a vaccine. That would be good. Or something that gets you over your infection faster so that you're not contagious for the same period of time. That would inhibit growth. Right now, by what we're doing, we are closing the pathway for that disease to move from one person to another. So you're at your home, I'm at my home, and but it does work. Unfortunately, another way that this inhibits the growth is when people die, because they don't infect anybody else when they're dead. So that sucks. But anyway, the smartest thing to do is to close off the pipeline. Another thing I would like to point out, and I hope you guys are watching the news and not just social media. You know, I listen to Governor Cuomo of New York, his daily soliloquy, and, you know, all of the task force things and all that stuff. But what you'll hear the Surgeon General say very often, or a lot of other people, especially the medical personnel, they say we're going to flatten the curve. We're going to, the other day they said inflection. I thought that was good. That's a calculus kind of term. But I'm just trying to plant a bug in your ear. Okay, so yeah, it's like Wrath of Khan. You ever see that movie? Okay, so remember whenever we have a parabola like that, and this was our maximum value, they want to flatten the curve. That's where it's flat, is at the very top, where it changes direction, starts going down. They would like it to go like this. So there's all kind of math terms being used. But now you know the formula to figure out uninhibited growth. So if we didn't keep away from one another, we know what we can anticipate for the state of Pennsylvania. But since we are staying away from one another, maybe that number will be less. The other thing, though, is testing. I mean, some people don't have symptoms, and not everybody's tested, so it's not a perfect number for the infections. It's not super accurate, but it'll be interesting to see. Anyway, I put some problems on CourseWeb a while ago. Practice problems on exponential growth and decay. I would like for you to please take a look at the ones involving growth for now, okay? And I'm going to turn this off, and I'm going to make a second part to this that'll be about exponential decay. So stay tuned. I really miss you guys something awful. This is so funny. Okay, see ya.